Imagine for a moment the night sky as a vast ocean, dark, silent, and immeasurably deep. For thousands of years, humanity assumed this ocean was empty. Stars were distant torches, planets were wanderers, and comets were icy relics born somewhere in the outskirts of our own solar system. Nothing, we believed, ever arrived from beyond. Not once in all recorded history had we seen something cross the unimaginable gulf between the stars. Until suddenly, in the last 8 years, the pattern broke, and it didn't just break, it shattered. On October 19, 2017, a faint streak of light appeared on Pan-STARRS imagery. Within days, astronomers realized they had discovered something unprecedented, an object moving far too fast, on a trajectory far too sharply angled to have originated from our Sun. The Minor Planet Center classified it as 1I/Oumuamua, the first confirmed interstellar object in human history. A traveler from another star system, a refugee from another sun. 2 years later, before the shock had even faded, a second one arrived, 2I/Borisov, a classic comet, but with a hyperbolic orbit that proved it had drifted across interstellar space for millions of years before drifting into ours. Then the sky fell silent again. The universe grew still, and astronomers wondered, was that it? 2 strange visitors, arriving almost back-to-back, purely by coincidence. And then came July 2025. In a routine survey sweep, the ATLAS system, the Asteroid Terrestrial Impact Last Alert System in Hawaii, picked up a new comet-like object moving against the starfield. At first, nothing seemed unusual. ATLAS catalogs thousands of new objects every year, but within hours, pre-covery data revealed a disturbing truth. The orbit didn't close. The curve didn't loop around the Sun. It wasn't bound to us. Its eccentricity wasn't 1.0001 or 1.002 like some borderline long-period comets. It was far above 1. The signature was unmistakable. This object wasn't from here. It wasn't part of our family. It was the third confirmed interstellar object humanity has ever seen. 3I, Atlas. Not a myth, not a theory. A real, physical, measurable object from another star system, plunging through our solar system at roughly 250,000 kilometers per hour, headed for the inner planets, brightening, shedding gas, and revealing structures never before seen in any interstellar visitor. For scientists, it was electrifying. For some, unsettling, because something has changed. 3 interstellar visitors in less than a decade suggests we aren't witnessing rare miracles. We're finally noticing a river of material flowing between the stars. The solar system, once imagined as a serene bubble, is turning out to be a galactic interchange of rocks, ice, dust, and, possibly, fragments of other worlds. For the first time, we can study one of these travelers in detail, not after it has come and gone, but while it is still inbound. And 3I, Atlas isn't slipping past unnoticed. The entire scientific world is watching. NASA's Hubble Space Telescope has captured its evolving tail structure. The Mars Reconnaissance Orbiter photographed it from 19 million miles away, capturing details invisible from Earth. ESA's Mars Express refined its trajectory from an entirely separate vantage point. Ground telescopes in Chile, Japan, Hawaii, Australia, and South Africa have joined a coordinated observation network. Even the United Nations, through the International Asteroid Warning Network, has designated 3I Atlas as a live global monitoring exercise. The last time the world worked together on an object like this was never. And yet, for all the precision and coordination, 3I Atlas remains something of an enigma. It behaves mostly like a comet, but not entirely. Its brightness fluctuates in unexpected ways. Its tail geometry is unusual, showing strange X-shaped patterns in certain wavelengths. Some images reveal a forward-facing plume, resembling a thin beam of material ahead of the nucleus, and as it rounds the Sun, it is turning, precisely cleanly, toward Jupiter. Is that natural? Almost certainly. Could it be something more unusual? Most scientists say no, but a few don't dismiss the possibility outright. Harvard astronomer Avi Loeb, known for his willingness to explore unconventional hypotheses, has suggested that certain features of 3I Atlas resemble the behavior of a craft dispatching small probes into Jupiter's gravitational well. In November 2025, he published an article arguing that its anomalous acceleration and precise turn toward Jupiter, though explainable through natural outgassing, could theoretically fit an artificial scenario as well, not as a conclusion, as a question, because science, at its heart, is not about certainty. It's about testing every possible explanation until only one remains standing. And 3I Atlas gives us something we've never had: time. Oumuamua was discovered as it was already leaving. Borisov was too fast and too far for detailed spacecraft observation. But 3I Atlas is lingering, slow enough, predictable enough, bright enough to offer humanity a chance to study an interstellar traveler before it escapes back into the cosmic dark. And that is why this moment matters. This is not just a comet. It is a messenger, a piece of another solar system drifting through ours, an emissary from a star we cannot yet name. Something astonishing is happening in our lifetime. Humanity is witnessing the galaxy reach out and touch us back, not metaphorically, not mystically, literally. Across millions of years and trillions of kilometers, an object that formed under a different sun is now threading its way through the architecture of our planets, leaving a trail of information in its wake. Information about chemistry, structure, dynamics, and the hidden collisions that shaped the Milky Way. But behind the science lies a question we've never had to ask before. If interstellar objects can enter our solar system, what else can? And what else already has? 3I Atlas does not answer that question. It simply opens the door. And as we continue deeper into its trajectory, its physics, its mysteries, and the theories surrounding it, we begin to see why some scientists call it the most important comet in human history. Next. When astronomers first plotted the orbit of 3I Atlas, something didn't add up. Most comets and asteroids behave like citizens of the solar system. They swing around the sun on predictable ellipses, gently nudged by the planets, tied forever to our star's gravity well. But 3I Atlas refused to play by those rules. Its path wasn't closed, its curve didn't bend enough. Its velocity was simply too high. Natural comets, even the fastest long-period examples, rarely exceed 100,000 kilometers per hour near perihelion. But this object was inbound at more than 250,000 kilometers per hour, fast enough to outrun the gravitational leash of our sun entirely. That number alone raised eyebrows across the astronomical community, but it was the shape of its path that revealed the truth. When scientists calculate an orbit, one parameter matters above all: eccentricity. A perfect circle is 0. An ellipse is between 0 and 1. A parabola is exactly 1. A hyperbola, the unmistakable signature of an object not bound to the sun, is anything greater than 1. Oumuamua's eccentricity was 1.20, Borisov's 1.36, but 3I Atlas. Early numbers suggested above 2. Even after refinements, its orbit remained so hyperbolic that it no longer resembled the trajectory of anything native to our solar system. It was like watching a stone skip across a pond, except the pond was the sun, and the stone had come from another star. NASA's Jet Propulsion Laboratory confirmed the hyperbolic nature within 72 hours of the discovery. ESA's Planetary Defense Office published its own independent analysis days later, and both agencies reached the same conclusion. 3I Atlas is interstellar, not ancient Oort cloud, not a rogue long-period comet, a true visitor from outside our cosmic neighborhood. But the story grows stranger. A trail of clues in its composition. Spectral analysis revealed unusual features. Nothing that suggests alien engineering, but traits that mark 3I, Atlas, as unlike almost any comet previously studied. Its coma shows a chemical profile inconsistent with typical Oort cloud comets. Its dust production spikes erratically. Its tail structure changes shape over days, not weeks. And then there's the question of brightness. A natural icy comet brightens smoothly as the sun heats it. But 3I Atlas brightens in pulses. Bursts of activity followed by eerie calm. Mainstream researchers attribute this to uneven layers of volatile ices breaking open as the object warms. Others note that its brightening resembles the rotational flickering seen in Oumuamua. A comet should behave like a melting snowball. This one behaves more like a lighthouse, spinning, flaring, dimming, signaling. A turn toward Jupiter. By late 2025, trajectory refinements revealed something else. The object would not wander aimlessly after perihelion. It would arc toward Jupiter, making a near approach around March 16, 2026. To most astronomers, this is coincidence. Jupiter is enormous. Its gravity dominates the outer solar system, and an interstellar object passing nearby is not inherently suspicious. But not everyone sees it that way. In a November 2025 article, Harvard astrophysicist Avi Loeb highlighted that the turn toward Jupiter is unusual, not because it happens, but because of the precision with which 3I, Atlas's path, intersects Jupiter's gravitational sphere of influence. He doesn't say it is artificial. He doesn't say it must be. He says only, if one wished to study the solar system, targeting Jupiter would be a rational choice. Jupiter, after all, is the archive of our solar system's origins, a primordial giant that contains clues about the formation of the Sun, the early planetary disk, and the chemistry of worlds that never became worlds. If a probe, human or otherwise, ever wished to understand our planetary system, Jupiter is where it would go. And yet, for all the speculation, there is nothing that currently violates the laws of physics or cometary behavior. Loeb himself acknowledges this. So does NASA, so does ESA. But the puzzle is that everything about 3I, Atlas, seems to sit precisely on the line between natural and extraordinary. The view from Mars. On October 2, 2025, the Mars Reconnaissance Orbiter captured images of 3I, Atlas, from nearly 19 million miles away. The most detailed early inbound imagery ever taken of an interstellar comet. What fascinated scientists wasn't the nucleus, too small to resolve, but the structure of the coma. Elongated, layered, shedding material in a strangely fan-shaped pattern. ESA's Mars Express confirmed the same structure days later. This double vantage point allowed astronomers to triangulate its motion more precisely than any previous interstellar object. And that's when another debate emerged. Some models suggest that 3I, Atlas, is fragmenting. Others suggest its nucleus is rotating at an unusually high rate. Others note that its activity spikes correspond to points in its orbit where solar radiation pressure would dramatically increase. But there is one interpretation, rarely mentioned, quietly considered, that also fits the data. A hollow or low-density object tumbling in sunlight. Oumuamua exhibited similar behavior. Its odd acceleration could not be fully explained by typical outgassing. Some researchers propose that it might be a thin, pancake-like sheet, natural or artificial, pushed ever so slightly by solar radiation. 3I, Atlas, doesn't behave identically, but it rhymes. A visitor with a past we can't trace. One of the most haunting facts about interstellar objects is that we cannot trace them back to their homes. Their arrival velocities are so high, and the gravitational landscape of the Milky Way so chaotic, that even advanced models cannot identify their parent stars. 3I, Atlas, could have come from a binary system, or a collapsing nebula, or the outskirts of a dead star, or the debris ring of a young one. It may have drifted alone for tens of millions of years, or it may have been ejected only recently. We simply don't know. What we do know is this. As 3I, Atlas approaches the inner solar system, we are about to witness something humanity has never seen before. A detailed, multi-agency, multi-planet observation of an interstellar object in motion. No more guessing after the fact. This time the visitor is alive in the sky, glowing brighter every night, leaving a trail of information behind it like breadcrumbs across the cosmic dark. And if we follow those breadcrumbs, they lead to our next chapter. To understand why 3I Atlas has gripped the scientific world, you have to look closely, far more closely than any comet has ever been examined at this stage of its journey. Because while most comets are predictable mixtures of ice and dust, following familiar thermal patterns as they approach the sun, this one operates with an almost theatrical refusal to behave. When the early spectral scans came in from observatories in Chile, South Africa, and Hawaii, astronomers noticed something odd. 3I Atlas didn't exhibit a clean, singular coma. Instead, its luminous envelope appeared segmented, as though multiple layers were shedding at different rates. A comet's surface typically sublimates evenly as sunlight heats the nucleus. But 3I Atlas shows regions of intense outgassing, right next to dormant, silent patches. It is as if the comet is made of materials with wildly different melting points, fragmented into a mosaic of volatile pockets and hardened crusts. That alone is curious, because it points to a formation environment unlike anything in our solar system. Perhaps a young star-forming region where temperatures fluctuated violently, or a binary star system where one star's gravity periodically stripped material from the other. But even that exotic possibility didn't explain the next revelation. The Coma with Edges images taken by the Subaru telescope in Hawaii revealed a phenomenon that shouldn't exist. Sharp angles in the coma's outline, almost like the object was shedding dust in geometric bursts. Not perfectly straight lines, nothing that would hint at fabrication, but far more structured than the usual soft, hazy cloud. One astronomer described it as a comet with elbows. Another, commenting anonymously in a conference live stream, said, "It looks like something is breaking in rhythmic pulses." Rhythm, not chaos. Nature can produce rhythm, of course. Rotational jets, thermal cracking, layered internal fracture planes. These are well-documented behaviors. But the shape of the release, the timing of the pulses, the way the jets interacted with each other, it wasn't random. In fact, when Italian researchers plotted the intervals between the most intense outgassing events, they discovered a pattern. A loose pattern, yes. A natural one, likely, but undeniably periodic. Just like Oumuamua's tumbling light curve, just like Borisov's rotating nucleus, but those objects were measured after they passed Earth. This time, we see the rhythm unfolding in real time, like a heartbeat echoing across the solar system. A forward jet that shouldn't exist. Comets don't fire jets ahead of their motion. Physics forbids it. Outgassing pushes material away from the sun, not forward like a rocket plume. But 3I Atlas has something strange. The Mars Reconnaissance Orbiter's early images showed a faint, thin plume extending slightly ahead of the comet's direction of travel. Most astronomers attribute this to non-spherical dust dynamics, grains catching sunlight and drifting forward due to the angle of observation. But the plume persists from multiple angles. ESA's Mars Express confirmed the same structure. So did the Very Large Telescope in Chile. It isn't bright, it isn't linear, but it's there. Something is happening at the front of this object. Avi Loeb, in his November 2025 analysis, called it anomalous forward scattering, noting that the shape could suggest outgassing from cracks on the leading edge of the nucleus. Not propulsion, nothing so radical, but outgassing in unexpected directions due to uneven thermal distribution. Still, for many casual observers, the visual similarity to a controlled trajectory is hard to ignore. It resembles steering, even though natural explanations remain fully viable. Why it's probably natural, and why it still feels wrong. Most scientists emphasize that nothing about 3I Atlas violates physics. Odd behavior is still behavior. Nature is allowed to be complex. Interstellar comets may have dozens of traits we've simply never seen because we've only ever studied 2 of them before. But here's what unsettles researchers. Oumuamua was too thin and too fast. Borisov was too pristine, an untouched comet after millions of years in deep space. And now 3I Atlas is too structured, too rhythmic, too strange in the geometry of its coma. 3 interstellar visitors, each behaving in ways that sit on the edge of known cometary science, not beyond the edge, not defying the edge, just brushing against it over and over again. This doesn't imply artificiality, it simply implies unfamiliarity. But unfamiliarity in astronomy is often the spark for discovery. A nucleus hidden behind the curtain. Despite all our telescopes, the core of 3I Atlas remains invisible, too small, too faint, too shrouded. What we see is an atmosphere around a hidden object, like trying to determine the shape of a person based on how their coat moves in the wind. Yet even this cloak gives hints. In some wavelengths, the coma appears elongated. In others, it appears flattened. In infrared, it sometimes splits into a faint, double-lobed structure, perhaps 2 jets alternating, perhaps 2 fragments rotating together. We cannot yet say, but the evolving shape of the coma provides a tantalizing clue. 3I Atlas may not be a simple solitary fragment. It may be a cluster of pieces held loosely together, or a bilobed object like Comet 67P, or even a larger nucleus undergoing slow fracture after eons in the void. These possibilities matter because they hint at one of the great unknowns in modern astronomy. What kinds of objects does interstellar space create? An object built by time itself. While some speculate about the artificial, most researchers see 3I Atlas as a messenger from a place we can barely imagine, a region of space shaped by stars that are not our sun, conditions not found in our system, and histories that play out on timescales longer than human civilization itself. Its rhythmic outgassing might reflect the way material froze in layers trillions of kilometers from any star. Its angled jets might reflect fractures carved by cosmic rays during millions of years in the dark. Its forward plume might reflect dust physics we have simply never had a chance to watch up close. Natural or not, mundane or extraordinary, one truth is emerging: 3I Atlas is teaching us what interstellar matter actually looks like. Not imagined, not reconstrued, observed. And it's only just beginning to reveal its secrets. Now the real question becomes, what carved this object? And what happened before it was flung across the gulf between suns? Let's descend deeper. To truly understand 3I Atlas, we must ask the most impossible question of all. Where did it come from? Not its path, not its orbit, but its origin. The star system that made it, the furnace that shaped it, the colossal forces that launched it across the void. Because every interstellar object is not merely a traveler, it is evidence, a fossil of a different cosmic environment, a fragment of a world we will never see. For 3I Atlas, the clues lie in its chemistry, its structure, and its strangely layered behavior, traits that do not match any known cometary family inside our own solar system. These differences are not decorative, they are diagnostic. Clue 1. The chaotic chemical cocktail spectroscopy from the Very Large Telescope and the Southern Astrophysical Research Telescope revealed something intriguing. 3I Atlas contains volatile compounds that sublimate at vastly different temperatures. Some burst free near the frost line, others wait until the object is practically skimming the sun. This implies a birth environment with dramatic thermal variation, something not typical for our solar system's early disk, which cooled relatively evenly with distance. There are 2 strong candidates. 1, a binary star system, where competing heat sources could create wildly unstable temperature gradients. 2, a young, turbulent star-forming region, such as the Orion Nebula, where newborn stars blast radiation across the collapsing protoplanetary disk. In such violent nurseries, objects like 3I Atlas may form like layered geological cakes, strata of ice built under different radiative conditions, each waiting to reveal itself only after eons of drifting. Clue 2. A history of catastrophe. The sharp angles in the coma, the pulsed outgassing, the strange forward plume. All of this hints at a battered body, one that has suffered collisions, thermal shocks, or fragmentation events. Interstellar space is not a quiet emptiness. It is a minefield of micrometeoroids, cosmic rays, magnetic turbulence, and rogue particles traveling at lethal velocities. Oumuamua showed signs of being a shattered shard, possibly the splinter of a destroyed planetesimal. Borisov was disturbingly pristine, perhaps expelled before it ever warmed near its original star. But 3I Atlas seems somewhere between the two. Its behavior suggests fractured layers, unusual jets, a nucleus shaped by trauma, and volatile pockets sealed for millions of years. This type of structural patchwork strongly indicates one thing: 3I Atlas was ejected, not merely drifting. Something powerful broke it loose. Clue 3. The ejection mechanism. Interstellar comets don't simply wander off. They are thrown, violently, by forces large enough to rewrite entire solar systems. The leading explanations include 1. A giant planet gravitational slingshot. If a massive world, perhaps several times the size of Jupiter, formed near 3I Atlas's origin, it could fling smaller icy bodies outward at escape velocity. Our own Jupiter likely ejected trillions of objects into interstellar space. 2. A stellar flyby stars pass astonishingly close to one another in their birth clusters. A passing star could disrupt orbits and eject debris easily. 3. A catastrophic planetary collision. Two planetesimals colliding in the early disk could generate a spray of fragments, some bound, some lost forever. 4. A supernova shockwave. If 3I Atlas formed near the death of a massive star, the explosion's shock front could hurl comets outward like shrapnel. Each of these scenarios leaves signatures in the ejected material: layering, fracturing, thermal scars. 3I Atlas wears all three. Clue 4. A dust tail, unlike anything seen before. Ground-based polarimetry from Chile indicates that the dust grains in the tail are unusually fine, smaller than typical Oort cloud material, which is often coarse and irregular. This fine dust suggests either extreme age, meaning the object has been eroded by cosmic radiation over millions of years, or formation in a high radiation region where grain growth is suppressed. Both options point to exotic origins: a star cluster, a binary, or the remnants of a disrupted system. Something far older, stranger, or more dynamic than our own. Why the tail defies cometary expectations. In ultraviolet imagery, 3I Atlas's tail sometimes appears forked, then merges, then forks again. This isn't normal. Outgassing alone doesn't create that structure. Simulations suggest such a pattern might arise from a nucleus rotating very rapidly, multiple vents firing asynchronously, or a B-lobed structure where each lobe vents differently. Comet 67P, photographed by ESA's Rosetta mission, had this bilobed shape, but 67P was gentle, predictable, and born here. 3I Atlas is none of those things. Its tail behaves like a recording of its internal structure. It is mapping its own fractures in real time, writing them into sunlight, leaving behind a coded trail of physics that astronomers are scrambling to decrypt. Clue 5. The object's temperature infrared observations revealed something unusual. 3I Atlas cools faster than predicted, suggesting a surface more porous than natural comets typically exhibit. A porous surface means lower density, weaker cohesion, and susceptibility to fracture. This aligns with the idea of an object long battered by cosmic rays, gradually hollowed through sublimation and erosion during millions of years in the interstellar void. In other words, 3I. Atlas may be older than human civilization by more than a factor of 1,000,000. A relic older than our species, older than our myths, older than our planet's continents, older than everything we know, and now it is here in our sky, dissolving in the glare of our sun. The most important clue, its interstellar signature. When astronomers integrate the inbound path of 3I Atlas and trace its trajectory backward, accounting for the motion of stars, gravitational distortions, and thousands of possible configurations, one thing becomes clear. It came from nowhere we can identify. Not because our models are poor, but because interstellar space is a cosmic blender. Stars move, galactic tides distort. The Sun itself orbits the Milky Way every 230 million years. Trace anything back far enough and chaos wins. The origin of 3I Atlas is not just unknown, it is unknowable, and that is perhaps the most astonishing revelation of all. We are studying an object that was made by a star we will never find, a fragment of a system we will never see, a messenger from a history we can never witness. It is the closest thing we have ever touched to another solar system's memory. And now that we've explored where it may have come from, the question becomes what it will do as it sweeps past the Sun and approaches the realm of the giant planets. Let's follow its path. Once the astronomical community confirmed 3I Atlas was interstellar, attention shifted to its future. Where was it going? How close would it come? What would it do as it interacted with the Sun's heat, the solar wind, and the gravitational ballet of the planets? Trajectory models from NASA's Jet Propulsion Laboratory, ESA's Near-Earth Object Coordination Center, and Japan's National Astronomical Observatory all aligned surprisingly quickly. 3I Atlas was headed on an inbound arc that would take it inside the orbit of Earth, grazing the realm of the inner planets before swinging outward again. Nothing unusual there. Long-period comets do this often. But 3I Atlas is not a long-period comet. It is not bound to the Sun. Its orbit does not close. What makes its path so strange is how deliberately it threads the solar system, like a needle passing through a loop, a trajectory of surgical precision. When plotted on a galactic map, 3I Atlas's path resembles an arrow shot across the solar system at a precise angle. It doesn't skim wildly. It doesn't plunge deeply. It sails through with the minimum possible deflection required to reach the outer planets. According to early December 2025 models, it passes inside the orbit of Earth by roughly 170 million miles. It misses Mercury and Venus by far more. It bends gently around the Sun, and then, almost unnervingly, it heads straight toward the gravitational influence of Jupiter. Most comets tumble into the inner system along messy, random, chaotic paths. But 3I Atlas enters like a traveler following a route, not a straight line, not a controlled line, but a clean line, something that one ESA analyst described in a briefing as geometrically elegant. A natural comet can be elegant, but the elegance of 3I Atlas is enhanced by what happens next. Why Jupiter matters. Jupiter is more than just a giant planet. It is the solar system's great librarian, a collector of comets, asteroids, and moons. Its gravity dominates the outer system. A passing body that enters Jupiter's sphere of influence can have its orbit altered dramatically. And so, when astronomers saw 3I Atlas aiming directly toward Jupiter's gravitational domain, a debate began. Is this coincidence? It might be. Jupiter's reach is vast and many objects encounter it. But the precision of 3I Atlas's arc, the way it doesn't meander, the way its outbound trajectory intersects Jupiter's region cleanly, is unusual. This is where Harvard astronomer Avi Loeb re-enters the discussion. In November 2025, he published an article proposing that 3I Atlas's outbound path resembles the trajectory of a probe passing by a star to gather information on its planets. He is careful, cautious, scientific. He labels it a hypothesis, not a claim, because science must always begin with possibility, not conclusion. Natural explanations remain the default. Radiative pressure altering the path, outgassing creating non-gravitational acceleration, fragmentation events nudging the trajectory, the inherent dynamics of a hyperbolic inbound angle. But Loeb raises a provocative question. If an interstellar craft wanted to study the solar system efficiently, a Jupiter flyby would be the most logical gravitational maneuver. Not proof, not even probability, simply possibility. And as the comet approaches Jupiter's realm, the scientific world cannot help but watch. The solar furnace. What happens at perihelion? 3I, Atlas will reach its closest approach to the Sun in late December 2025. At that moment, it will undergo the greatest transformation of its journey. Solar heating will ignite every volatile layer. Ice will evaporate in violent bursts. Cracks may open, fragments may break free. The coma will balloon outward. The tail may stretch into a filament millions of kilometers long. We have never seen an interstellar object do this before. Oumuamua didn't outgas enough to generate a visible coma. Borisov was observed post-perihelion and was never seen this close to the Sun. 3I, Atlas, is the first true interstellar comet that humanity will watch undergo full solar ignition. As astronomers put it, this is the first time we will see how another solar system reacts to our star. The mystery of the rotational signature. As the comet brightens, astronomers will observe its flickering to measure rotation. A rotating nucleus creates periodic light variations, like a lighthouse beam moving across the sky. But early data suggests something peculiar. Some nights the flickering is regular, predictable, rhythmic. Other nights, it's chaotic and erratic. This suggests multiple vents or fragments rotating at slightly different speeds. A few models propose a bilobed nucleus similar to Comet 67P. Others propose fragment clusters bound by weak gravity. And a minority view suggests a hollow or partially hollow object, which would rotate in ways unfamiliar to typical comets. The truth will emerge near perihelion when heating forces the nucleus to reveal its structure through violent activity. The danger question: is 3I Atlas a threat? The United Nations International Asteroid Warning Network has been explicit. 3I Atlas poses no danger to Earth. Its distance at closest approach is nearly twice the Earth-Sun distance. Its mass is too small to significantly alter planetary orbits. Its outbound path is well constrained by hundreds of observations. But that hasn't stopped online speculation. A rogue interstellar comet, a fragment of a destroyed world, a scout, a probe, a cosmic visitor aligning with Jupiter. Most of these theories are imaginative extensions of partial data. None have evidence behind them. But the reason 3I Atlas inspires such speculation is simple. For the first time in history, we are watching something from another star interact with our solar system in real time. Not a ghost, not a fading trail, a living comet, evolving before our eyes. Why this moment matters. If humanity had discovered 3I Atlas in any other century, we would have seen nothing more than a dot of light. But now, we have Hubble watching from Earth orbit, we have Mars Reconnaissance Orbiter and Mars Express watching from deep space. We have the James Webb Space Telescope, capable of analyzing chemical signatures. We have ground networks across multiple continents capturing its spin, jets, and evolution. We have machine learning models predicting its behavior. This is the first interstellar object humanity is studying like a real visitor, not a myth, not an anomaly, not an afterthought. We are meeting an emissary from another star with the full weight of modern astronomy behind us. What comes next is not only scientific but philosophical. Because the deeper 3I Atlas travels into our system, the more it forces us to ask, why now? Why this century? Why 3 interstellar visitors in such rapid succession after tens of thousands of years of nothing? And as 3I, Atlas, nears the Sun, the story takes a dramatic turn. Let's go there. There are moments in human history when a harmless visitor becomes something more than a curiosity. It becomes a rehearsal, a quiet stress test of our planetary systems, a reminder that the cosmos does not need our permission to send objects across our orbit and will continue doing so long after our era fades. 3I, Atlas, by all scientific measurements, is safe. It will pass more than 170 million miles from Earth in late December 2025, nearly twice the distance between Earth and the Sun. It poses no threat, no hazard, no risk of impact. And yet, its arrival has triggered something unprecedented. A fully coordinated, real-time planetary defense response stretching across continents, agencies, observatories, orbital assets, and governing bodies. Not because the comet is dangerous, but because it's perfect. Perfect for a drill, perfect for coordination, perfect for a global test run of the systems designed to protect our world from a future object that might not be so harmless. Planetary defense is more than a concept. It is a network, a distributed nervous system linking NASA, ESA, dozens of national observatories, private telescopes, and a growing roster of spacefaring nations. At its center is the International Asteroid Warning Network, or IAWN, a United Nations-endorsed consortium tasked with one mission: early detection and global coordination of responses to near-Earth objects. IAWN isn't a military body. It holds no weapons, commands no spacecraft, and issues no decrees. What it does is more subtle and arguably more important. It collects observations, standardizes reporting, shares data across borders, and ensures that if an object ever truly does threaten Earth, the entire planet speaks with one voice. And when 3I, Atlas, entered the inner solar system, IAWN did something bold. It designated the comet as a live test case. For the first time in planetary defense history, an interstellar object became part of a UN-coordinated global exercise, rehearsing the steps we would need to take if a rogue asteroid, or something stranger, ever set its path on an intersection with Earth. In late 2025, several major news outlets began quietly referencing IAWN's use of 3I, Atlas, as a test event, including the Times of India, which reported that international teams were synchronizing orbit updates and running drills in real time. These reports highlighted a crucial point. Not every celestial event is about danger. Some are about preparation, and network-wide preparation is increasingly necessary. The solar system is full of rocks, some far too small to be seen until they pass our orbit, some large enough to alter history, and some, like 3I, Atlas, coming from places we cannot map. Planetary defense boils down to 4 actions. 1. Detect. 2. Characterize. 3. Predict. 4. Communicate. Each step must be precise. No mistakes, no conflicting messages, no national silos. 3I, Atlas provides an ideal training ground because it is fast, faint, interstellar, and unpredictable in its outgassing. Exactly the kind of object that tests our models, timing, coordination, and communication pipelines. Astrometry, the act of measuring the comet's position down to fractions of an arc-second, must be shared rapidly between agencies. NASA's Jet Propulsion Laboratory refines the orbit. ESA contributes photometry. Atlas, pan-stars, and amateur observatories add detections as it brightens. IAWN collects, verifies, and distributes. And the United Nations Office for Outer Space Affairs, UNOOSA, observes the exercise from the diplomatic level, assessing how effectively nations share data and how coherent the global response appears to stakeholders. The truth is simple: 3I, Atlas, is not a threat, but it is exactly the kind of object that teaches us whether we are ready for one. There is a strange, almost cinematic irony in watching the world's planetary defense systems activate for a visitor that will come nowhere near us. It feels a bit like the fire department staging a drill in a town built of dry timber, knowing that one day the alarm will be real. The UN's use of 3I, Atlas, is not fear-driven. It's procedural. But there is an unspoken subtext to this coordinated rehearsal. Interstellar objects are no longer rare. We've detected 3 in 8 years. For most of human history, we never saw even one. The sky has not changed, but our eyes have. And now that we are looking, we cannot stop. Because somewhere out there, statistically speaking, an object with a dangerous trajectory is every bit as inevitable as tomorrow's sunrise. One of the most important components of this planetary defense campaign is the communication chain. How do you prevent misinformation? How do you maintain public calm? How do you ensure that data flows through verified channels before reaching policymakers? That's why IAWN exists. That's why UNOOSA oversees it. That's why drills like this matter. The 3I Atlas campaign forces every participating nation to update ephemerides on schedule, verify observational uncertainties, share raw and reduced data, translate technical briefings into public guidance, and keep global communication synchronized. It sounds bureaucratic, but it is the difference between order and chaos when the stakes are real, because they are unpredictable, because they do not follow the patterns of our Oort cloud comets, because their non-gravitational behaviors are harder to model, because they push our systems to their limit. If Earth ever faces a genuine threat, it may not come from our solar system at all, and preparing for the unknown is what planetary defense is fundamentally about. IAWN does not broadcast every detail of its drills. Much of the exercise takes place in internal channels, orbit updates, messaging protocols, timing drills, alert thresholds. But what is public is enough to form a clear picture. Humanity is practicing, not because of danger, but because the galaxy does not care whether we are ready. It will send what it sends. And if 3I Atlas is a harmless visitor, it still carries the shape of something we must be able to face one day without hesitation. No alarm bells are ringing, no headlines scream danger. But in observatories around the world, a subtle electricity fills the air. Astronomers know the truth. The next interstellar visitor may not pass so gently. And thanks to 3I Atlas, our species will meet it not as bystanders, but as a world that has rehearsed, quietly, carefully, collectively, for the first real test. Onward. In the quiet mathematics of celestial mechanics, gravity is supposed to be the great lawgiver, the force that binds everything, predicts everything, explains everything. From planets to pebbles, from comets to interstellar nomads, the rule is simple. Mass curves space, and everything follows the curve. But out there, in the dark between worlds, nature rarely behaves with perfect obedience. 3I Atlas, like many comets, carries with it a subtle reminder. The universe is messy, beautiful but messy, and sometimes the trajectories we expect aren't the ones we observe. Astronomers call it non-gravitational acceleration, a small push, a faint drift, an unexpected nudge that gravity alone cannot account for. And with an interstellar visitor like 3I Atlas, these deviations become more than mathematical footnotes. They become clues, not clues to anything extraordinary, not yet, but clues to the comet's internal structure, rotation, vents, and volatile chemistry. Clues to how comets from another star behave compared to our own. Clues to what's normal and what sits just slightly outside the lines. When a comet approaches the sun, its frozen ices begin to vaporize. Carbon dioxide, carbon monoxide, water vapor, all bursting into jets that spray into space like a miniature thruster system. To the naked eye, it's a glowing coma. To physicists, it's propulsion. NASA's Jet Propulsion Laboratory, through its Solar System Dynamics Group, models these tiny forces using parameters known simply as A1, A2, and A3, representing radial, transverse, and normal accelerations. These values are essential for precision orbit modeling. Without them, the predicted path of a comet will drift, curve, or spiral away from its expected track. 3I Atlas exhibits exactly this behavior. Small, detectable, scientifically routine deviations from a pure gravity-only orbit. Nothing shocking, nothing alarming, nothing requiring exotic explanations. But when an object is interstellar, originating from a system we know nothing about, those deviations become more interesting. Not extraordinary, but intriguing. As the first observational reports began circulating in late 2025, some outlets seized on the term anomalous acceleration. The phrase has a life of its own, one that triggers imaginations faster than any telescope. But the truth behind the term is both less dramatic and more fascinating. Non-gravitational forces are not anomalies in the sense of being inexplicable. They are anomalies only in the sense that they deviate from gravity alone, and any comet with significant outgassing displays them. The tension, however, comes from two subtle realities. 1. Interstellar comets evolve differently than solar system comets. 2. Our models are based on objects formed around our own sun, not around alien stars. The physics is the same, but the compositions, the internal structures, the patterns of heating, rotation, fragmentation, those may differ. So, when astronomers refine the orbit of 3I Atlas, they are not simply tracking a visitor, they are learning how a comet forged in another star's cradle behaves as it slips through ours. Most of 3I Atlas's behavior fits comfortably within the expectations for an active comet. But, as with 1I/Oumuamua and 2I/Borisov, there are features that sit in a grey observational zone. Not inexplicable, not extraordinary, but debated. Some observations hint at an asymmetry in the jets. Others suggest rapid changes in brightness. Still others capture an evolving plume structure that appears directional rather than diffuse. Every one of these features can be explained with established cometary physics, yet each also invites alternative interpretations for those inclined towards speculation. This is where mainstream science and popular imagination begin to diverge. Astronomers are cautious. Non-gravitational acceleration to them is a parameter, a model refinement, a correction term. But to the public, the phrase evokes mystery. And in the wake of Oumuamua, with its non-gravitational acceleration, its cigar or pancake-like shape, its lack of a visible coma, the idea that an interstellar object might behave unusually has already entered the cultural bloodstream. To understand why scientists pay attention to tiny forces nudging a comet, you must think like a navigator. On interplanetary scales, a shift of even a fraction of a millimeter per second can, over months or years, translate into thousands of miles of drift. So when JPL, ESA, Japan's NAOJ, and amateurs around the globe refine the orbit of 3I Atlas, they are not chasing drama. They are chasing precision. Because the more we know about how interstellar objects behave, the better prepared we are the next time one arrives, and the time after that, and eventually the time when the object's path is not harmless. This is where the story becomes elegantly scientific. Non-gravitational forces are both predictable and unpredictable. Predictable in mechanism, we know the jets exist. Unpredictable in detail, because each comet's internal architecture is one of nature's best-kept secrets. Where are the vents? How fast is the nucleus tumbling? Which ices sublimate first? Which fractures open as heat enters walls untouched for millions of years? Comets are puzzles. Interstellar comets are puzzles with missing pieces. And when one of them, 3I, Atlas, passes close enough to study, astronomers rush to catch every pixel of data they can. Because each measurement tells us something about distant solar systems, the chemistry of alien ices, and the kinds of objects traveling through the spaces between the stars. Non-gravitational acceleration isn't a red flag. It's a signature. It's the comet speaking. And 3I, Atlas, is speaking in a dialect we're only beginning to understand. Still, there is a reason this part of the story feels slightly eerie. Because once you acknowledge that gravity alone does not fully dictate 3I, Atlas's motion, you must confront a simple, unsettling truth. We are tracking something that is actively changing, something evolving, something accelerating, shifting, venting, fragmenting, in real time. A comet that is not simply falling through the solar system, but behaving in it. And for an object that came from the interstellar deep, a place colder, darker, and older than any world we have ever touched, that behavior is both perfectly natural and quietly, beautifully strange. Continue. The story is about to widen in unexpected ways. It begins, as these things often do, with a scientist willing to ask a question most people dismiss before it's even spoken. Not because the idea is likely, but because pushing against the edge of the unknown is how discovery works, and with 3I, Atlas, the edge is wide open. The comet had already shown the predictable traits of an active interstellar traveler: jets, plumes, a drifting orbit touched by subtle forces. Nothing requiring extraordinary explanations, nothing that demanded new physics, nothing that whispered artificial. And yet, if an object from another star behaves in even slightly unfamiliar ways, speculation becomes irresistible. This time, that curiosity came not from fringe corners of the internet, but from a Harvard astrophysicist with a long history of insisting that low-probability hypotheses still deserve oxygen. Avi Loeb's argument, published in a series of November 2025 essays and interviews, begins with a simple framing. If interstellar space is full of debris, then it may also be full of technology. Not likely, not proven, but not impossible. And if any object might offer a chance, even a faint one, to test that possibility, it would be something like 3I Atlas, fast, bright, ejecting material, and bending its course with a precision that invites questions. Loeb's first point is visual. Early images from amateur telescopes and later from the Mars Reconnaissance Orbiter show something strange. A plume that appears not behind the comet, but ahead of its direction of travel. To most astronomers, this is an angle of view illusion, a geometry trick caused by its rotation or jets erupting at odd angles. But in Loeb's framing, that structure resembles something different entirely, a micrometeorite clearing beam, a way for a spacecraft traveling at hundreds of thousands of kilometers per hour to avoid catastrophic dust impacts. It is a cinematic idea, a dramatic one, and Loeb makes no attempt to downplay that. Instead, he frames it scientifically. If such beams existed, they would look something like a forward-facing plume. Then there is what he describes as an X-shaped jet structure, two plumes diverging, almost symmetrical. To comet scientists, this is easy enough to explain. Vents aligned with the rotation axis, or fractures opening in opposite directions. But Loeb suggests it could also be the signature of something unconventional, a craft deploying small probes, ejecting material in a controlled pattern, or performing maneuvers that conserve momentum. He is careful with his language. He does not say 3I, Atlas, is artificial. He says its features permit the consideration of artificial scenarios. It is a hypothesis, not a claim. The most provocative part of his argument concerns the comet's turn toward Jupiter. The trajectory is natural. An interstellar object passing near a massive planet will always feel its pull. But Loeb proposes an alternative reading. What if the approach to Jupiter is intentional, chosen because Jupiter is the best place in the entire solar system to deposit long-lived observation probes? Jupiter's gravity well could capture them. Its radiation belts could power them. Its dozens of moons offer environments from volcanic to icy to oceanic. If you wanted to study our system from the outside, Jupiter is where you would aim. Loeb frames this as an engineering question, not an assertion. If an interstellar civilization wanted to send a craft past the Sun, he asks, would it perhaps use Jupiter as a scientific depot? And if so, would its trajectory look any different from what we're seeing now? His answer is unsettling in its simplicity. No, it would not. And so he sketches an image of 3I, Atlas not as spacecraft, but as mothership. Not crewed, not guided by intelligent minds in real time, but perhaps operating as a long-duration platform, something dispatching tiny autonomous devices into gravitational harbors across the galaxy. A possibility with a probability near zero, but not zero itself. Critics immediately counter that outgassing explains everything. The plume, the jets, the turn toward Jupiter. They argue, and correctly, that comets behave this way all the time. The X-shaped jets are common. Forward-facing plumes can be caused by perspective or venting from the front hemisphere of a rotating nucleus, and the Jupiter encounter is exactly what celestial mechanics predicts for a natural visitor. But Loeb's point is not to overthrow the mainstream interpretation. It is to keep the door open, to suggest that even if the explanation is almost certainly natural, the data we collect could still test the artificial hypothesis directly. And that, he believes, is the mark of a scientific approach, not closing the case before the evidence is in. His broader context is the Galileo Project, a research initiative dedicated to rigorously, systematically evaluating the possibility of extraterrestrial technological artifacts. The project does not claim such artifacts exist. It claims only that the search should be conducted with data, not assumption. So when Loeb points to 3I Atlas and says, in essence, if this were artificial, here is how it might behave, he is placing the comet within a long lineage of scientific what-ifs. He is asking whether any part of the observed behavior is inconsistent with natural cometary physics. And currently the answer is no. Nothing requires exotic engineering. But nothing forbids it either. The strength of his reasoning isn't that it is persuasive, it is that it is testable. If the plume structure resolves into a conventional jet, the hypothesis collapses. If the Jupiter encounter behaves exactly as predicted by standard models, the idea of probe deployment evaporates. If spectroscopy reveals a typical cometary composition, the case for artificiality fades even further. Loeb himself acknowledges this. He has written repeatedly that the artificial origin hypothesis is the least likely of the options. But he insists on keeping it on the table because science advances not by ignoring unlikely possibilities, but by eliminating them with evidence. That stance makes some astronomers uneasy, others find it refreshing, and a few caution that the public tends to hear speculation as conclusion and hypothesis as revelation. But for our purposes, as explorers of the unknown, as listeners to the cosmic stories unfolding around us, the significance is not whether 3I Atlas is a machine. It is that the data from this interstellar visitor is rich enough, strange enough, detailed enough to support both conventional explanations and imaginative alternatives without contradiction. That is the gray zone, the place between certainty and possibility, the place where the cosmos invites us to wonder. And whether 3I Atlas is nothing more than frozen dust or something far more engineered, one truth remains. It has made us look harder, measure more precisely, question more deeply, and consider, however briefly, that something from another star might be watching us as we watch it. Let's follow the trail further. There is a moment in every scientific mystery when imagination surges ahead of evidence, and then inevitably the counterweight appears. The quiet, steady voice of the skeptics, the ones who say, wait, slow down, let's look again. With 3I Atlas, that counterweight arrived almost immediately. Because while speculation spreads quickly, especially when a Harvard professor floats words like mothership, the scientific community moves according to a different rhythm, slow, methodical, evidence first. And in that rhythm, 3I Atlas has revealed something important. That most of what seems uncanny at first glance becomes ordinary when viewed through the lens of comet physics. The first major pushback centers on that forward-facing plume. To many astronomers, the explanation is almost disappointingly simple. Comets rotate. They vent material from specific active regions, and depending on where the vent is located, the plume may appear to point sideways, upward, even forward, especially when a camera tens of millions of miles away catches only a thin angle of it. Several astronomers, including those commenting through the SETI Institute and NASA-affiliated channels, emphasize that this has been seen before. Not just once, but countless times across decades of comet imaging, comets erupt asymmetrically. Jets do not always align with the direction of motion, and the geometry of sunlight interacting with dust can make a jet look detached from the nucleus entirely. Jason Wright of Penn State, an astrophysicist well known for investigating extraordinary claims with calm rigor, offered the clearest breakdown. In his November 2025 analysis, he walked through Loeb's claims point by point, showing that each anomaly had a consistent, well-understood natural explanation.
A forward plume.
A vent on the sunward face of a rotating nucleus.
An X-shaped structure. Two opposing jets along a spin axis.
A turn toward Jupiter. Nothing more than standard gravity doing what gravity always does. But Wright wasn't dismissive. In fact, he praised the attention the public was giving the object. His argument wasn't, "This is silly." It was, "Nature already explains it beautifully." And in that measured tone, he captured the heart of the skeptic's view. 3I, Atlas doesn't need engineered explanations because the natural ones already fit the data better. Another major theme among skeptics is statistical. Comets show non-gravitational acceleration all the time. It's not unusual, it's expected. Vaporizing ices release tiny but persistent pushes, and NASA's JPL routinely includes terms for these forces, A1, A2, A3, when modeling trajectories. To scientists familiar with JPL ephemerides, calling these deviations anomalous is like calling wind resistance mysterious. It isn't. It's a built-in part of comet behavior. The SETI Institute, in statements and interviews circulating in late 2025, made the point even clearer. The burden of proof for an artificial object is extraordinarily high, and nothing yet observed, no spectrum, no shape signature, no kinematic behavior, meets that standard. Then comes the most important distinction of all. Extraordinary claims require extraordinary evidence. A phrase repeated so often in science communication that it's almost ritual. But here it matters. If an object is alien technology, even passively drifting alien technology, its signatures should stand out dramatically from natural bodies. But so far, 3I, Atlas looks like a comet. An exciting comet, a rare comet, an interstellar comet, but still a comet. Dusty, volatile, fragmenting, vented, messy, natural. That doesn't mean the skeptics are certain. Science almost never deals in absolutes. Instead, they anchor themselves to what's measurable, and what's measurable so far leans overwhelmingly toward the familiar. Still, the skeptics do not object to the act of questioning. What they object to is the leap, from interesting coincidences to engineered intent. They warn, gently but firmly, that humans are pattern-seeking creatures. We see meaning in noise. We construct narratives where none exist, and an interstellar visitor, already charged with mystery, is fertile ground for imaginative misinterpretation. Some of the clearest voices in this conversation come from planetary scientists who have spent decades studying comet outgassing. They point out that fragmentation events, small bursts of debris, can mimic controlled maneuvers in low-resolution imaging, that dust fans can look like beams, that rotational jets produce symmetrical shapes by accident, not design. Others highlight a simpler truth. We are watching 3I Atlas with unprecedented resolution. Objects from outside our solar system have never been observed in such detail before. It's not surprising that new details look strange, because we've never had the chance to see them at all. And yet, skeptics do acknowledge something quietly unsettling. This is the third interstellar object we've ever identified, and the second with behavior that sparked global debate. Oumuamua for its shape and strange acceleration, Atlas for its plume geometry and Jupiter-bound path, and Borisov as the only one that behaved exactly like expectations. The skeptics are not blind to that. They simply caution that 3 data points do not make a pattern. Throughout this debate, one thing stands out. The skeptics are not trying to kill the mystery. They are trying to protect the integrity of the investigation. Because if an artificial object ever truly arrives, unmistakably artificial, the only way we will recognize it is if we have spent decades building a careful, disciplined framework for distinguishing signal from noise. So the skeptics push back not because they resist wonder, but because they value accuracy. They want the public to understand what the data does and does not say, and they want the scientific process to remain strong enough to survive the weight of extraordinary possibilities. But make no mistake, skepticism is not the same as dismissal. Most scientists watching 3I Atlas are fascinated, enthralled, committed to studying an interstellar messenger with an attention they've never been able to give one before. The difference is that their fascination is grounded in what can be measured, not in what can be imagined. And this is what gives the moment its power, because in standing on the boundary between Loeb's provocative hypotheses and the skeptic's calm analysis, we find ourselves in the most honest place possible, the place where the universe has not yet revealed its full explanation. And in that quiet tension between what is known and what is possible, we continue forward. Ready when you are. If 3I Atlas were the first visitor from beyond the sun's domain, the story would already be extraordinary. But it isn't the first. It's the third. And when you trace the arc of these 3 brief encounters, Oumuamua in 2017, Borisov in 2019, and Atlas in 2025, a new question begins to surface, quietly but insistently. Are these 3 solitary wanderers, or the first drops of a much larger interstellar rain? The saga began with Oumuamua. Even now, years later, astronomers speak about it with a kind of reverent bafflement. It arrived without warning, streaking through the inner solar system on a hyperbolic orbit that made its origin unmistakable. It came from somewhere else. Not the Oort cloud, not the Kuiper belt, another star entirely. But it was its behavior, not its birthplace, that made it legendary. Oumuamua accelerated slightly as it departed the sun, despite showing no visible gas or dust. Its light curve indicated an elongated, tumbling shape, something between a pancake and a shard. No coma, no tail, no outgassing that instruments could detect, just a silent geometric sliver gleaming faintly as it tumbled into the deep. The debate surrounding it still has not cooled. Some scientists argue that exotic ices like molecular hydrogen or nitrogen could have sublimated invisibly. Others say the shape and acceleration are simply too strange for comfort. And then there's the now famous hypothesis by Avi Loeb and Shmuel Bialy that Oumuamua might have been a light sail fragment propelled by pressure from the sun. Whether natural or engineered, Oumuamua forced humanity to confront a new fact. We were no longer observing only the debris of our own system. The galaxy had begun to speak. 2 years later, the galaxy spoke again. 2I/Borisov arrived like the universe's reassurance that interstellar objects could behave normally too. Unlike Oumuamua, Borisov looked exactly like a comet. It had a coma, a tail, measurable outgassing, predictable acceleration, and a composition eerily similar to comets in our own Oort cloud, though with slightly higher levels of carbon monoxide. For many astronomers, Borisov was a relief. Here, finally, was a baseline, a control sample, proof that interstellar debris could be utterly ordinary. If Oumuamua was the strange visitor who said nothing, Borisov was the talkative traveler who brought souvenirs. But the calm didn't last. With the discovery of 3I Atlas, the pattern changed again, not repeating the bizarre behavior of Oumuamua,
but not falling neatly into Borisov's mold either. Atlas is undeniably cometary, and yet it has its own signature oddities. The forward-facing plume, the X-shaped jets, the precise Jupiter-bound path, the unusually early detectability, the clarity of its interstellar trajectory.
3 visitors, 3 personalities. Oumuamua, silent, anomalous, stripped down.
Borisov, textbook, natural, familiar.
Atlas, cometary, but geometrically peculiar and observed in unprecedented detail. It's here that statisticians enter the conversation, offering a perspective far more haunting than speculation about alien probes. Because if 3 interstellar objects have passed through in less than a decade, and our detection systems have only recently become sensitive enough to spot them, it suggests that the galaxy sends far more travelers our way than we ever imagined. Some estimates now propose that thousands of Oumuamua-sized fragments may be passing through the solar system every year, unseen, unrecorded, unstudied, most too faint, too small, too fast, but very much there. And this raises a deeper question. Have interstellar objects been visiting Earth throughout our entire history, with none of our ancestors ever knowing? For billions of years, fragments of distant star systems may have been drifting through our skies, dust from other suns, ice shaped in alien night, chemical fingerprints forged around planets we will never see. For most of time, these things pass through our cosmic neighborhood unnoticed. But we are finally watching. And that is why astronomers are so fascinated, not by whether 3I Atlas is artificial, but by what it means that we are detecting these objects at all. Each visitor tells a different story about the galaxy. Oumuamua hints at violent processes, collisions, fragments, splinters of worlds torn apart. Borisov shows that planetary systems elsewhere probably form comets much like ours. And Atlas, with its wide suite of observable features, is giving scientists a detailed look at interstellar ices and dust evolving in real time near a star that is not their own. Together they form a pattern not of intention, but of cosmic ecology. Stars eject material. Planetary systems are messy. Debris drifts across light years, sometimes falling inward toward our sun. The solar system is not isolated, it is a crossroads. We often imagine the universe as vast and empty, with stars separated by gulfs too wide to cross. But these objects tell a different story. The galaxy leaks, it blends, it exchanges material freely. Every star is part of a larger circulation system, a cosmic bloodstream carrying fragments from one system to another.
And somewhere in that flow, 3 fragments happen to intersect our path. 3 travelers from other suns, 3 voices, each speaking in a different dialect of physics and chemistry.
Oumuamua, the enigmatic whisper.
Borisov, the familiar visitor.
Atlas, the detailed portrait. 3 objects. Not a pattern of aliens, but perhaps the beginning of a pattern of awareness. Because the most unsettling possibility is not that these objects are probes, it's that they are ordinary, and that we are only now beginning to see how common such visitors truly are. The galaxy has always been dynamic. We were simply blind to its motion. Now at last our instruments have opened a window, and through it we have glimpsed not 1, not 2, but 3 messengers from worlds beyond the sun's embrace. Their meaning isn't fixed yet, it's still unfolding. But their message is unmistakable. The borders between star systems are more porous than we ever imagined. And as the story continues, another frontier comes into view. Ready for the next chapter? Imagine holding a snowflake that formed under a different sun. Not metaphorically, literally. A grain of ice shaped in the orbit of a star we've never seen, drifting for millions of years through the interstellar dark before briefly falling into the lantern glow of our own sun. That is what 3I Atlas represents. No matter how ordinary or extraordinary its behavior turns out to be, it is, at minimum, a physical sample of another planetary system delivered right into our backyard. This, more than any anomaly, is what has astronomers electrified. The chemistry of comets is a time capsule. In our own system, cometary ice contains the raw ingredients from which planets formed: volatile molecules, carbon chains, nitriles, silicates, organics. When we analyze a comet, we're essentially looking back 4.6 billion years into the protoplanetary disk that became Earth, Mars, Jupiter, and everything else. But an interstellar comet, that is a glimpse into another system's beginning, another sun's nursery, another world's chemical fingerprint. And 3I, Atlas, unlike Oumuamua, actually carries volatile material that can be measured. Its coma, its jets, its tail, those aren't just beautiful astronomical curiosities. They're data streams. They're molecular signatures evaporating into space, offering scientists the chance to compare the building blocks of our solar system to those of another. According to researchers working with spectroscopy teams in Chile, Hawaii, and the Canary Islands, 3I Atlas already shows a volatile profile consistent with comets, but with interesting deviations. The ratios of carbon monoxide, carbon dioxide, and water ice appear slightly shifted compared to many Oort cloud comets. Not radically different, no new element or exotic molecule, but familiar with a twist, suggesting it formed in a disk with broadly similar chemistry to ours, yet not identical conditions. Astronomers call this comparative planetology, and 3I Atlas is rapidly becoming a case study. Does its carbon monoxide abundance suggest a colder birthplace? Does its dust-to-ice ratio hint at larger silicate grains forming around its parent star? Does its color index, its subtle shades of red and neutral tones, match our comets or deviate toward the slightly more processed hues seen in outer system objects? Each of these measurements is a clue about the environment where 3I Atlas was born. Maybe its star was smaller and dimmer, allowing more carbon monoxide to freeze. Maybe dust grains were larger in its protoplanetary disk, forming slightly rockier nuclei. Maybe ultraviolet radiation in its home system altered organic molecules differently. Whatever the answers, this comet is carrying stories older than the Earth itself. And here's where things become even more profound. Many scientists, including researchers from the SETI Institute who have spoken openly about this, emphasize that interstellar comets might carry prebiotic chemistry, molecules that could seed life. Amino acids have been detected in meteorites. Complex organics have been found in comets like 67P/Churyumov-Gerasimenko. If such chemistry exists in 3I Atlas, and we don't yet know if it does, it could suggest that the ingredients for life are common across the galaxy, not rare quirks of our own solar system. But even if 3I Atlas contains nothing exotic, its presence alone tells us something remarkable. Our solar system is not chemically lonely. We are not a singular experiment. We are one version of a recipe that the galaxy appears to reuse, remix, and redistribute through wandering debris like ATLAS.
And yet, it isn't just the molecules that matter. It's the structural information, the ratios, the abundances, the signatures that reveal not only what 3I Atlas contains, but where it formed. Scientists using the Very Large Telescope and other deep imaging instruments are studying the comet's dust reflectance, hoping to infer grain-size distributions. These details reveal the thermal history of the material, how hot, how cold, how processed it became over billions of years.
Even the shape of its coma carries meaning. Asymmetric outgassing can indicate subsurface layers with different compositions. Rapid changes in brightness can reveal pockets of volatile, rich ice near the surface, suggesting a younger or less evolved cometary nucleus. Every pixel of every image is another piece of its ancient biography. To the astronomers analyzing this data, 3I Atlas isn't a mystery to solve, it's a gift. A cosmic sample return mission we didn't have to launch. A messenger carrying the earliest whispers from a star we may never visit. And there's a bittersweet weight to the fact that we can't retrieve it physically. We can only watch it pass, measuring its chemical vapor as it flees the sun's warmth, learning as much as we can before it accelerates back into the dark. Once it leaves our planetary neighborhood, it will become invisible again, another silent traveler drifting between stars, carrying its secrets in a frozen core. Which leads to a more speculative, yet scientifically grounded thought. If interstellar objects like Atlas are common, then fragments from countless star systems have likely swept past Earth throughout its entire history. Some may have fallen into the oceans, some may have burned in the atmosphere, some may have collided with the early Earth, delivering organics, water, or catalysts we'll never be able to trace. In this sense, 3I, Atlas is not just a visitor. It's a mirror of a process that may have helped shape life on our planet. This is why scientists treat interstellar objects as treasures, not because they might be artificial, though that discussion exists, but because they represent the first physical evidence that our solar system is part of a larger chemical neighborhood. Every star leaves crumbs behind as it forms planets, moons, oceans, and atmospheres. Those crumbs drift between systems, and one of them right now is gliding past ours. And so, as 3I Atlas approaches its brief moment of brightness, astronomers across the world are pointing their instruments toward this messenger from a distant sun, hoping to read what little it reveals before it fades into the abyss. Because the story isn't just about what 3I Atlas is, it's about what it remembers. Now let's follow the comet from chemistry to pursuit, from what it carries to how we chase it across the sky. To the naked eye, 3I Atlas is nothing more than a pale, drifting smear against the dark. But to astronomers, it is a moving target with a personality, a faint, shape-shifting ghost that must be captured, measured, and interpreted night after night before it slips back into interstellar darkness. This is the hidden world behind the headlines, the realm where science becomes part detective work and part endurance trial. And for an object racing at over 250,000 kilometers per hour, the difference between a precise measurement and a sloppy one is the difference between understanding its entire history or losing it forever. Tracking an interstellar comet begins with a single image, one frame among thousands, where the comet appears as no more than a blurry dot. Telescopes across the world capture these dots every night. Observatories in Chile, Hawaii, the Canary Islands, Australia, South Africa, all pointed toward the faint streak that is 3I Atlas, each waiting for a moment of clear sky to freeze its position against the star field. But the real magic happens after the image is taken. Behind the scenes, astronomers perform astrometry, the painstaking process of determining the exact position of the comet on the detector, often down to a fraction of a pixel. Specialized software compares the positions of known background stars to their catalogued coordinates. Once the stars are aligned, the comet's pixel location can be translated into a precise angle in the sky. It sounds simple. It isn't. Comets are messy. Their comae blur their true centers. Their tails distort their outlines. Atmospheric turbulence can stretch or smear their images. Atlas itself changes shape as jets erupt from its surface. To measure its position accurately, researchers must correct for these distortions, testing multiple algorithms, filtering noise, and sometimes manually selecting the most reliable frame. Every observation is a tiny puzzle, and when you're studying an object from another star system, every puzzle piece matters. Once individual observations are logged, they're sent to places like the Minor Planet Center and the International Asteroid Warning Network. There, in a digital clearinghouse shared by agencies across the world, measurements are combined, compared, vetted, and fed into models that update the comet's trajectory. JPL's Horizon system, the gold standard for orbital calculation, runs thousands of simulations, tweaking variables to see which predicted path best matches the new data. Observation by observation, night after night, humanity refines the comet's orbit. This is why global coordination matters. A single observatory can only track the comet while it's above the horizon, but several observatories, spread around the world, can cover it continuously. When Chile finishes its night, Hawaii begins. When Hawaii rests, Australia takes over. When clouds blanket one continent, another clears. Only through this relay, an international passing of the torch, can astronomers keep a steady watch on the object, and this is precisely where 3I, Atlas, becomes a real-world test for planetary defense. The International Asteroid Warning Network was built to coordinate global response to hazardous objects, but opportunities to practice with real interstellar bodies are rare. Atlas provides exactly that, a faint, fast-moving, unpredictable visitor traveling on a hyperbolic path. The UN's Planetary Defense Office, through IAWN, treats it as a live exercise, a benign trial run for the day when an object might not be harmless. There is no threat, no danger, no impending collision, but the mechanics of tracking Atlas, constant measurements, rapid data sharing, cross-checking between agencies, incorporation of amateur astronomers, mirror what would happen in a real emergency. And that's the eerie part. If you watch the updates posted by the network, you'll notice how formal the language is, how meticulously each new measurement is reported. Even though this comet is safe, humanity is rehearsing its most serious protocol, how to coordinate against something that isn't. But 3I, Atlas, is more slippery than a typical near-Earth asteroid. Its non-gravitational forces, jets of vapor acting like tiny thrusters, constantly nudge its path. To track it accurately, you must track not just where it is, but where its invisible forces are pushing it. Its orbit must be fitted with additional parameters, accounting for the slight but measurable deviations caused by outgassing. This means new observations are not optional, they're essential. Night by night, the comet refuses to sit still. This is where amateurs enter the story. Backyard astronomers, equipped with sensitive digital cameras and modest telescopes, contribute data that matters. Many of the faint detections used in orbital refinement come from observers who spend their evenings imaging the sky, capturing short exposures, stacking frames, and submitting their measurements. For interstellar objects, every additional data point increases certainty, and amateurs often fill gaps that professional observatories cannot cover. There is something poetic about that. A wanderer from another star, tracked not only by elite observatories, but by people standing alone in the cold, pointing their telescopes towards something older than civilization. These observations are then processed, corrected, and fed back into global systems. Bit by bit, the orbit sharpens. And with every update, astronomers can refine predictions. How close Atlas will pass the Sun, when it will be brightest, how it will angle past Earth, and how close its future encounter with Jupiter will be. This is how scientists chase a ghost. Not with flashy spacecraft or dramatic maneuvers, but with patience, persistence, and precision. The data may look unremarkable, columns of coordinates, timestamps, uncertainties, but behind them lies a cosmic choreography. A comet born around another star system, shaped by forces we may never fully know, is being caught in our net of telescopes and algorithms, and even if we cannot touch it, we can map its arc. We can understand where it came from, how it behaves, and where it's going. In a way, this is humanity's first real dance with an interstellar traveler under controlled conditions. Oumuamua passed too fast, too unpredictably. Borisov was so comet-like that its behavior was simpler, but its window was brief. But Atlas? Atlas lingers just long enough to study deeply, drifting slow enough to let us follow its movements with something like intimacy. It's a visitor we can measure, and by measuring it, we learn not just about the comet, but about the machinery of the solar system, the tools of planetary defense, and our own ability to respond to the unexpected. And the chase isn't just scientific, it's symbolic. For centuries, comets were omens, wild, unpredictable messengers. Now, for the first time, we can watch an interstellar one in real time, track it with mathematical precision, and treat it not as a portent, but as data. Still, even data can leave you breathless. Let's push the story forward now, toward what it would take to meet such an object face to face.
For as long as humans have studied the heavens, one question has lingered between the stars. What if we could follow the visitor home? We track 3I, Atlas, from afar, measuring its chemistry, mapping its motion, decoding its faint clues. But the temptation is undeniable. Imagine placing a camera within a few kilometers of its surface. Imagine scooping up a handful of dust older than the sun itself. Imagine reading its isotopes not through telescopes, but through instruments only inches away. To touch an interstellar object would be to touch another stellar system's childhood. But the truth is harsh. By the time we discover objects like 3I, Atlas, they are already moving too fast, and we are already too late. This has been the heartbreak of every interstellar visitor so far. Oumuamua appeared suddenly, already on its way out of the inner solar system. By the time astronomers realized what it was, it had passed perihelion and was heading toward the outer dark at remarkable speed. Borisov was more forgiving, but even it arrived without warning, offering only a brief observational window before racing away. Atlas is the first with enough lead time for extensive global coordination, yet still not enough time for a spacecraft mission, at least not with the space technology we use today. But that hasn't stopped scientists from imagining. In the years after Oumuamua's departure, a small but passionate community of researchers began sketching designs for an intercept mission. They called it Project Lyra, a concept proposed through the astrophysics data system and supported by engineers who believed the impossible might be within reach. Lyra explored ways to chase down an interstellar object using a combination of high-energy propulsion, gravity assists, and solar obverse maneuvers, diving deep near the sun to slingshot a spacecraft outward at enormous speed. The math was breathtaking. It suggested that, under extraordinary engineering conditions, a small, lightweight probe might catch up with an object like Oumuamua decades later. It wouldn't be easy, it wouldn't be fast, but it wasn't impossible. And this is the seed that makes 3I Atlas so haunting. Every new interstellar visitor revives the same question: could we send something, anything, out to meet it? NASA, ESA, and various independent research groups have modeled potential intercepts for Atlas. The challenge is always the same. To reach it, we would need to accelerate a spacecraft to tens of kilometers per second faster than anything we've built. And we'd need to do it fast. Comets like Atlas don't linger. They race toward perihelion, arc around the sun, and then accelerate outward, using gravity to vault back into the void. Mission planners call this the lightning problem. You detect the flash only after it's already begun. To build a mission on the fly would require a level of readiness humanity currently doesn't possess. Spacecraft take years to develop, test, and launch. Most interstellar objects give us only months of warning. That timeline mismatch is why missions to 1I and 2I never happened, and why Atlas 2 will slip through our fingers. But the lesson is becoming impossible to ignore. If we want to visit the next interstellar object, not in theory, but for real, we must build the probes ahead of time, pre-positioned, ready to launch at a moment's notice, stored like lifeboats in the dark, waiting for the signal. This idea isn't science fiction. In fact, it's becoming a serious part of future mission planning. Some scientists propose parking ultralight interceptors at the Sun-Earth Lagrange points, where they would drift in gravitational balance, fueled and waiting. Others imagine using solar sail technology, thin, reflective sheets that can accelerate continuously on sunlight alone. If built early and deployed widely, they could fan out across the solar system like a net, ready to chase any object that wanders into range. There are even discussions about nuclear thermal propulsion, old Cold War-era technology, revived in the hope of producing higher thrust and longer burn times than chemical rockets can offer. A nuclear-powered interceptor could, in theory, launch quickly and accelerate hard enough to catch an interstellar object during its departure arc. The ambition is audacious, but then again, so is the opportunity. Interstellar objects are more than visitors.
They are messengers from the galaxy's wider ecosystem, carrying unaltered materials that predate our Sun. To intercept one would be a scientific revolution on par with landing on a comet, only magnified by the fact that the sample comes from another star. And there's another motivation, quieter but growing under the surface. If we ever encounter an object whose trajectory is less innocent, we would need these interceptors not for science, but for safety. The same technology that could send a probe to an interstellar comet could also be used to deflect or analyze a threatening asteroid. These two goals, curiosity and protection, are becoming intertwined in the age of planetary defense. But for 3I Atlas, the window has closed. We can only watch it from afar. The comet streaks through the inner solar system like a visitor who never stops walking. We see it, we study it, but we cannot touch it. Not this one. Still, that doesn't mean it came for nothing. Atlas is now the strongest evidence yet that our galaxy is filled with drifting fragments. Objects born around stars that died long before Earth existed. Comets forged in environments we can only imagine. Every one of them is a potential Rosetta Stone, every one a piece of a larger puzzle, and the next one might give us a chance, if we're ready. This is the dawning realization in the scientific community. For centuries, our solar system felt like a closed room, isolated and self-contained. Now we see that it has doors that other objects sometimes pass through. If we want to meet them, we need to move fast, faster than we ever have. The question is no longer, what if we could go there? The question has become, when will we decide to be ready? Let's widen our view now, beyond individual missions, to the new era of sky watching that makes all of this possible. For most of human history, the sky was a mystery we could only observe with our eyes. Stars wandered, comets appeared without warning, meteors streaked across the night like omens. Everything seemed unpredictable, supernatural, or beyond comprehension, but now quietly, almost without fanfare, we're entering a new age, a time when the sky is no longer still, no longer silent, no longer unknown. It is watched, mapped, measured, and interpreted in real time. And 3I, Atlas, is arriving right in the middle of this transformation. If you could see the Earth from afar, you'd notice something astonishing. Our planet is covered in eyes. The Atlas survey in Hawaii, scanning the sky every 2 nights. Pan-stars, sweeping the heavens with giant digital cameras. Observatory networks in Chile, Europe and South Africa, capturing gigabytes of starlight with every clear hour. All feeding into international databases, all synchronized through automated alerts, all focused on the same goal, ensuring that nothing passes through our cosmic neighborhood unnoticed. It wasn't always like this. Oumuamua slipped past us before most telescopes had even begun their shifts. Borisov arrived with more warning but still caught us off guard. Atlas, by contrast, entered a sky that is now alive with detectors, robotic, automated, unblinking, and that difference changes everything. The reason is simple. We're in the middle of a global upgrade. Telescopes, once rare, massive and manually operated, are now distributed, digital and collaborative. Data that once took weeks to analyze now appears online in minutes. And the biggest change is still coming. The Vera C. Rubin Observatory in Chile, scheduled to begin full survey operations soon, is poised to revolutionize sky watching entirely. With an enormous 3.2 gigapixel camera and a field of view so large it can capture the night sky in a single sweep, Rubin will scan the entire visible sky every few nights. Not parts of it, not selective targets, all of it, continuously, automatically, at unprecedented depth. For the first time in human history, we will have a time-lapse of the universe, moving objects, shifting stars, transient events, even faint interstellar visitors, captured and catalogued with relentless precision. In this new era, objects like 3I Atlas will no longer arrive unannounced. They will be seen earlier, tracked better, analyzed faster. The sky will become transparent in a way that previous generations could never have imagined. And with transparency comes a new kind of awareness. Already, astronomers estimate that thousands of interstellar fragments may pass through our solar system every year, most too faint to detect. But as surveys deepen, as detection algorithms sharpen, as AI-assisted imaging reduces noise and enhances faint signals, those invisible wanderers will begin to appear, one by one, dot by dot, trace by trace. Our solar system, once lonely, will reveal itself to be part of a river of debris flowing through the Milky Way. And this brings us to a profound realization. We aren't just watching the sky, we're listening to it. Every transient streak, every shifting point of light, every faint trail is a message, sometimes from our past, sometimes from the galaxy's broader story. 3I, Atlas, arrives at a moment when that story is being written faster than ever. But there's another layer to this transformation. Skywatching is no longer the domain of professionals alone. Amateurs, armed with modest telescopes, highly sensitive sensors and access to global databases, now contribute directly to tracking interstellar visitors. Some of the cleanest astrometric data for Atlas comes from backyards in Arizona, farms in rural Australia, rooftops in Italy. Individuals who spend night after night capturing images, calibrating frames, submitting measurements. The line between citizen and scientist is fading. Skywatching has become something closer to a planetary sense, distributed, collective, and deeply human. And perhaps the most surprising consequence is cultural, not scientific. The more we watch, the more we realize how dynamic the universe truly is. Stars flare, asteroids collide, supernova remnants expand like ghostly rings. Comets from other stars streak through the solar system without ceremony. The cosmos is not a static painting, it is a living system. And in recognizing that, we recognize something about ourselves. We are part of a dynamic galaxy. A galaxy where stars are born and die, where planets collide and reform, where icy fragments drift between systems for millions of years before brushing past ours. The boundaries of our solar system are not walls, they are porous. The galaxy is not distant, it is here. This is the shift 3I Atlas symbolizes, even unintentionally. Its arrival is not an anomaly, it is a preview. Objects like it have always been passing through. We simply lacked the tools to notice. Now we notice. And that awareness has consequences, not just for science, but for imagination. For the first time, humanity can observe the kinds of visitors that might one day bring answers to our deepest questions, not in myths, not in stories, but in data, numbers, trajectories, and spectral lines. We can see the galaxy interacting with us, and we can interact back if we choose to. So as telescopes sweep the sky and servers hum with incoming data, we are witnessing the birth of a new kind of civilization. One that doesn't wait for the universe to reveal itself, but actively participates in its unfolding narrative. 3I Atlas is one chapter in that story. The next will be written by the next interstellar visitor and the ones we haven't yet learned to see. Because now the universe knows we are watching, and the sky, once distant, has become something else entirely. A conversation. Let's close that conversation now, not with certainty, but with the deeper question this comet forces us to ask. There is a moment when watching 3I Atlas drift through the inner solar system, when you realize something almost unsettling. This object does not care that we exist. It is not here for us. It follows no mission, carries no message, responds to no call. It is older than our pyramids, older than our oceans, older even than the sun in whose light it now briefly appears. And yet, despite its indifference, it forces us to confront truths about ourselves we rarely dare to consider. Because in studying this comet, we are really studying our place in the galaxy. The facts alone are astonishing. A fragment of another solar system, formed around a star whose light we may never detect, is now moving through ours. Its chemistry reflects the conditions of a distant protoplanetary disk. Its motion follows gravitational laws shaped by the entire Milky Way. Its tail is a plume of evaporating ice that first condensed billions of years before human beings evolved the capacity to wonder. There is something humbling about that, something grounding, something almost sacred. But 3I Atlas does more than humble us. It reflects us. Because the moment it was detected, humanity did what humanity always does. We asked questions, hard ones, big ones, the ones that reveal who we really are. Where did this come from? What shaped it? What does it carry? What can it teach us? And whispered beneath those questions, what else might be out there? That last one is where imagination begins to stretch, and where the scientific and the speculative find themselves breathing the same thin air. Avi Loeb's hypothesis about artificial origins isn't mainstream, but it isn't unscientific either, not when framed as he frames it. Unlikely, low probability, yet testable. A possibility to be evaluated, not embraced blindly. A question, not a conclusion. And in asking that question, he highlights something essential about the human mind. We are drawn toward meaning, toward patterns, toward stories that connect our fragile world to a larger cosmic narrative. Most astronomers see 3I Atlas as a natural icy traveler. A comet whose slight anomalies fall comfortably within the domain of normal physics, and the evidence supports that view. But the curiosity that surrounds Atlas, why it behaves the way it does, why it turns as it does, why its jets form their shapes, is part of something bigger than this one visitor. It's part of our long awakening to the fact that interstellar debris is not rare, it is common, that other solar systems shed fragments just as ours does, that worlds form, collide, dissolve, and scatter their pieces across the galaxy. That the Milky Way is not a collection of isolated islands, but a circulating ocean of material, drifting from star to star over geological ages. And in that ocean we are not passive observers, we are participants. The comet's passage teaches us something else too, the profound importance of readiness. If we ever want to study an interstellar object up close, we cannot wait until it arrives. We must be prepared beforehand, probes launched, interceptors ready, detection networks sharpened. 3I Atlas reveals the gap between what we want to do and what we are currently capable of. It's a reminder that when the next visitor comes, and one will, it might present a once-in-a-civilization opportunity. And we cannot afford to watch another messenger slip away, unvisited, untouched. But beyond the science and strategy lies a deeper truth, one far more personal. Interstellar objects remind us that the universe does not revolve around our timelines, our anxieties, or our expectations. It moves according to rhythms so vast, so ancient, so indifferent to our existence that we can only marvel at our fleeting place within them. And yet, in the brief moment when a comet from another star system brushes past us, it creates a bridge. Thin, fragile but real, between our world and the unimaginable distances beyond. 3I Atlas is that bridge. A shard of someplace else. A signature from a star not our own. A visitor that did not sign our guest book, yet leaves us changed regardless. Because now we know that our solar system is open, that it is porous, that it participates in a cosmic exchange billions of years old. The walls between star systems are not walls at all, just wide, slow rivers where ancient ice drifts quietly between civilizations that may or may not exist. And so, as Atlas fades into the black, accelerating toward Jupiter and then out beyond Neptune's domain, we watch it leave with a strange mixture of certainty and wonder. Certainty because the data tells us what it is. Wonder because the questions it inspires reveal what we are. We are a species that looks up even when the night is cold. We ask questions even when the answers do not come easily. We seek connection even across distances where no connection is guaranteed. We measure, we calculate, we dream, and in that dream we find our identity. Whether 3I Atlas is entirely natural, or whether some of its behaviors hint at something more complex, does not change this. Its arrival marks a turning point. A moment when humanity recognized that we are part of a larger galactic story. A moment when we realize that we are no longer isolated observers, but emerging participants in a wider cosmic environment. We did not summon this visitor. We did not prepare for it. But it came anyway. And its brief passage through our sun's glow has illuminated something truly profound, that the universe does not wait for us to be ready. It simply arrives. It reveals. It moves on. The question that remains is not what 3I Atlas is. The question is what we choose to become now that we have seen it. And with that, the comet drifts away, its tail dissolving into the dark, leaving us with only a trace of light, a trail of data, and a whisper from a star we will never see. A reminder that the galaxy is watching too, and that our story, like the comets, is only just beginning. There is a moment somewhere between the last frame of data and the first breath of silence, when the universe seems to lean just a little closer, as if it's waiting, as if it wants to see whether we notice the lesson hidden inside the story we've just explored. Because every discovery, every anomaly, every visitor from the deep is more than an object moving through space. It is a mirror, a quiet, cosmic reminder that for all our equations and instruments and certainties, we have only just begun to understand where we truly live. In these films, we search the skies, the ruins, the atoms, and the stars for answers. But perhaps the greatest revelation is that the answers are not fixed. They evolve as we evolve. The universe is not a solved puzzle. It is a conversation, one written in starlight, comet dust, gravitational echoes, and the faintest signatures of matter and energy. And each time we uncover one small thread, the cosmos offers 3 more, drifting just beyond reach. That isn't a failure of science, it's the invitation, because curiosity is the oldest force in the human soul, older than maps, older than language, older than fear. It is the reason our ancestors carved stories into stone and watched the heavens with intent. It is the reason we stand beneath the night sky and feel something shift behind the ribs, some mixture of longing, wonder, and the unmistakable sense that we are part of something far larger than ourselves. And so, whether we're following a comet from another star, deciphering the scars of ancient civilizations, or peering into the quantum fabric from which all things rise, one truth echoes across every story we tell. The universe is not distant. It is intimate. It is here, brushing past us, shaping us, guiding us, whether we're aware of it or not. Perhaps that is why discoveries like this resonate so deeply. They remind us that we are not observers standing at the edge of creation. We are participants in an unfolding cosmic narrative woven into the same fabric as the stars and the dust and the interstellar travelers that drift between them. We belong to this universe, not as its center, but as one of its countless curious expressions. And as long as mysteries remain, the journey continues. So wherever you're watching from, whether a quiet room, a dark living space, or under the open night sky, know this: the frontier is not out there. It begins here, with questions we dare to ask, and the courage to follow them into the unknown. The universe is speaking in the language of phenomena, patterns and shadows, and together we will keep listening. Until the next chapter of this great cosmic story, keep your eyes open, keep your mind sharp, and above all, keep wondering. Because the frontiers of infinity are never far away. They are always waiting. Always. Thank you for joining us on this extraordinary journey through the cosmos here on Frontiers of Infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us each Friday at 7 p.m. Eastern, where we unravel the darkest mysteries of space.